Hi everyone. So today we're going over springs in energy, whereas yesterday we did centripetal motion in energy. So we're going to add back springs to our energy problems. So we have this block traveling with a velocity towards an unstretched, uncompressed spring at equilibrium. Then it is going to compress the spring a certain distance before it comes to rest. Given the information we have, the block is 0.8 kilograms. The spring has a spring constant of 50 newtons per meter. There is friction along the surface with a coefficient of 0.5. What is the maximum compression in the spring if the velocity is 1.2 meters per second right as the block makes contact with the spring? Okay, so let's do a COE for this. Okay, we've got there's no gravitational potential, right? It's not changing its height. So we've got kinetic, we've got spring potential, and that will equal the final kinetic, the final spring potential, and any work taken out due to friction. Well, if it comes to rest to see maximum compression, right, that would go out as rest. Here, our spring is at equilibrium. That's a ZPL. So let's break this down. We've got 1/2 mv naught squared equals this potential of a spring is 1/2 kx squared plus mu nd. So if this is on just a flat surface, there's no other forces, normal force will just equal mg. So normal force is mg. The distance traveled is also the distance compressed, so we'll just call everything x. So let's rewrite this as 1/2 mv naught squared equals 1/2 kx squared plus mu mgx. Now, you might think this is going to be kind of complicated because we've got to solve for x. But we've got two x's. That's going to be a pain in the rump. So we've got to do something that's never really fun. For physics, we're going to subtract that over, so you have 1/2 kx squared plus mu mgx minus 1/2 mv naught squared. And now you notice that you've got an x squared here, you've got an x here, and then you have no x here. So if this is giving you PTSD from math class, that's because we're going to have to do a quadratic. This is essentially 0 equals ax squared plus bx plus c. Only your c now is negative, and your a, b, and c are all complex variables multiplied together. So what you can do is to get the quadratic, right, you have x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. If your math teacher didn't have you sing that all the time to the tune of Pop Goes the Weasel, I apologize. That's a part of your math development that you just missed out on. Now, we have an A, a B, and a C. Our A is right here, 1/2 K. Our B is going to be mu mg, and our C is negative 1/2 mv squared. So what you could do is write this all out. You could have x equals negative mu mg plus or minus the square root of mu mg squared minus 4 times 1/2 k times negative 1/2 mv naught squared, all under the square root, divided by 2 times 1/2 K. That you could do, and then you could put in all of your numbers and then hope for the best that you put in all the parentheses right on your calculator. However, what I would recommend is instead get a value for A, for B, and for C, and just plug those values in right here. So if you do that, let's get a value for all of these. That would be 25 for A. For B, let's see. You get 3.924 for B. For C, you get negative 0.576. So instead of doing this right here, we're going to just plug our numbers in directly. So we have x equals negative 3.924 plus or minus the square root of 3.924 squared minus 4 times 25 times negative 0.576 all over 2 times 25. If you put all that in your calculator correctly, you're going to use the plus instead of the minus on your square root. You would get 0.092 meters or 9.2 centimeters. So that is the distance that this spring is compressed if the mass K, mu, and V are all as such in that scenario. So that's how we can incorporate springs back into this, right? Remember that the spring potential energy is the same as the work done by a spring, which is 1/2 kx squared. The force by a spring is kx. Okay, so remember, don't get those too confused. Now let's talk about the methods that we're going to use. Okay, conservation of energy versus force methods. We talked a little bit last time in the centripetal and energy video about going back and forth between force and conservation of energy, knowing which one to use for centripetal scenario. Now for springs, this is a little bit easier to determine what you should do. Okay, so we've got this scenario over here. Okay, mass M is sliding down the ramp and compresses the spring K, and there is friction on the ramp. Now, let's talk about these one at a time. Okay, so we've got part A. What is the velocity of M at maximum compression? Well, that would be 0, right? It has maximum. It compressed that spring as much as it could. If it were moving, then it obviously wouldn't be the maximum, right? It has to stop at maximum. Now, what is B? What is the acceleration on M at maximum compression? Well, that would also be 0, right? At maximum compression, it's not going to be accelerating at that moment, right? It had negative acceleration as it slowed down. The moment it's done compressing, the acceleration is 0. Then the acceleration will begin to get more and more positive from there. So letter C, what is the net force when the block reaches maximum compression? So let's look at this. If we have maximum compression, right? Say we've got the force of the spring up the incline. You've got mg there. Let's say that the x and y is along the incline. So we've got a theta right there. So your force of the spring minus mg sine theta, that's all going to equal 0, right? We just established A is 0. So that means the force of the spring equals mg sine theta. Now, the net force when the block reaches maximum compression, okay, the net force is going to equal 0. Then part D asks, so can a force method find the maximum compression? The answer is no, right? Because if all we can see is that mg sine theta equals the force of the spring, that means that you basically just set the block there and let it just come to rest. Okay, it compressed the spring, but it's just coming to rest where now the block and the spring are at equilibrium. That's not what it's asking. The summation of forces can't account for the speed of the block and the friction as it's traveling, right? Can't account for all of that and how far the block could compress the spring, okay? Maximum compression, summation of forces cannot handle, okay? But how would a COE bail us out? So a COE could bail us out because that's all COE can find, right? COE, say, we've got we've got gravitational potential energy, we've got kinetic energy, we also have spring potential energy that equals UGF, KF, USF, and any work done by friction, right? So let's cancel some of this out. Let's call that ZPL. It's got to come to rest. Let's say it even started at rest. And the spring started at a ZPL. So then you've got your potential energy goes to spring potential and the work done by friction, right? That actually looks very similar to what we just did, only that was with kinetic energy, not UG naught. So this could tell you the maximum compression. Okay. If you want to know max compression, this is what you would use. However, if you wanted to know the final resting position, okay, what if we want to find the final resting position when the block stops moving entirely? Well, that is what this could tell you. So it's not that force is better or COE is better. It's that COE and force have their own uses and they can solve for different things. So depending on what the question asks, you will use one or you will use the other, right? So final resting position or max compression, two very different things that you will use either summation of forces or COE. All right, so we've got two practice problems. First, force or energy, which would we use? So we've got two blocks connected by a light string and a frictionless pulley. The system is released when the spring is unstretched, that is at equilibrium. The block then slides on a rough surface with friction. If M2 falls a maximum distance h, calculate the coefficient of kinetic friction from the block M1, right through here. Get mu k. So if we want to do this, okay, we're looking for the maximum distance, right? That is basically maximum compression. So let's see what we can get here. Okay? Maximum compression. We have gravitational potential from block 2. Everyone is starting at rest, but we'll go ahead and put it there. Then we have spring potential, no gravitational potential for 1, no spring potential for 2. I should put a 1 there. Then you've got UG2 final plus K2 final plus K1 final plus the final spring potential for the block 1 and any work taken out by friction. And remember, we want mu k. So this is the guy we're shooting for. Let's cancel some of this out. Let's say that the final height is the ZPL. If we're looking at the maximum compression, then it has to stop at rest. And it also says that we start with an unstretched spring. So I'm going to assume that's also starting at rest. I don't think that's actually explicitly stated, just hinted at. So that is also rest. Now it is unstretched. So that is an equilibrium. That's ZPL for the spring. So we've got the gravitational potential energy for block 2 turns into the spring potential for block 1, and there is work lost due to friction, right? So if we want to find this, what we do is we take mgh equals 1/2 kx squared plus mu n d. Okay? So here we know that normal force will equal mg on that flat surface. We also know that h will equal d, will also equal x. So you can just call them all h if you'd like. So let's rewrite this. We have mgh equals 1/2 kh squared plus mu mgh. And we were solving for mu. Let's see, an h can get on out of there. So we'll get rid of that. Let's solve for mu. Then you have mg minus 1/2 kh divided by mg. But I missed my m's. That is mass 2, as we can see there. This would be mass 1 that is losing that friction there. So we've got an m2 and an m1. That would all equal mu. m2g minus kh all over m1g. Now, so that's how we would be able to find that. If we had values, we'd be able to put all of that in and find our coefficient of friction. Now it asks, did you go with force or energy here? So we were looking at maximum distance. That's the key here. Force can't tell us maximum distance. Energy can. Now if it asked, where does the block come to rest at equilibrium, then we would use summation of forces. That's what that can tell us. COE has nowhere in here to tell us where does the block come to rest. That's not something that COE can really find for us. So last one. This is actually, we're actually going to do both here, just to prove our point, right? The block system shown is found at rest. How far from equilibrium has the spring stretched? Assume no friction. So we're just looking how far it stretched, it came to rest, okay? So here, okay, if we've got springs, okay, you would use summation of forces if the spring is stopped, okay, and it's motionless, meaning it's not in the middle of moving. You would use a COE if the spring is stopped and in the middle of motion. I guess technically it doesn't even have to be stopped, right? You could just find where in that compression does the spring exist. So it just needs to be in motion, right? If it's in the middle of its motion, whether it's maximum compression, maximum elongation, or somewhere in between, right? We actually went over that where you integrate from x naught to x final of the, what was that? Integrate negative kx dx, right? So we did that, right? We know how to do that. But this is asking, it's stopped, it's found at rest, and it's motionless. It's not in the middle of motion. So we can use summation of forces. This summation of forces is actually going to look similar. This is something we just looked at. And we will use the inclined plane as a basis for our x and y. Now that tension, okay, remember tension is a funny force where you can usually substitute something else for it sometimes. Here we would use the spring force for tension. So our summation of forces along the x, because that's where we defined that direction, right? That would be f of s minus mg sine theta, and it is found at rest, so that would be 0. So then we have kx minus mg sine theta equals 0, and we want the distance, right? Yep, how far from equilibrium. So x would equal, we add the mg sine theta to the other side and divide by k. So that's how you'd be able to find that if the block is found at rest, right? It's stopped and it's motionless. This is just how far from equilibrium does that block pull the string and come to rest. So that is what we would do for that. Now for the next part, it says with the spring unstretched, okay, at equilibrium, the block is allowed to slide down the hill. how far is the spring stretched from equilibrium when the block first comes to rest at the bottom? So if it starts at equilibrium and it starts sliding, how far from equilibrium does it first come to rest before it does its oscillations, right? So that's asking for maximum elongation of our spring. So let's look at this. We have a COE, right? Let's see, we would have gravitational potential energy, we would have spring potential energy, kinetic energy, and then we would have, we don't have any friction, right? Assume no friction. Good. So then we have the final spring energy, we have K final, and no friction. So that's everything we've got. Let's look. Wherever it lands, we'll call that our gravitational ZPL. It starts at equilibrium from the spring, that would be ZPL. It is released from rest, right? The block is just allowed to slide down, and we're looking at maximum elongation, so that is also rest. So rest for both kinetic energies. Okay? So all we are left with is UG naught equals USF. Okay? So we've got our MGH equals 1/2 kx squared, and we want to know x. That's what we want. We don't want the height, right? It didn't ask how far, what height change did it have. We want x. But what is h? Right, so let's look at this. Our theta is actually defined for us. It is relative to the horizontal. So this is our theta. Let's say it drops this distance x. That means our height over here would be x sine theta. So let's substitute that in for our h. We have mg x sine theta equals 1/2 kx squared. One of those x's can get right on out of there. And we just solve for x. Multiply by 2, divide by k. You've got 2 mg sine theta divided by k equals x. And if you pay attention, the only difference between these two distances where the block comes to rest and the maximum distance it travels is that 2. That is the only difference between the two. Everything else is just mg sine theta divided by k. So that's how we can use the force and energy methods to solve spring problems. Last time we talked about how force and energy can coexist with a centripetal motion. This is how force and energy can be used to solve spring problems. Right. Next video, we'll continue on through chapter 8 for just a couple more videos, and then we will wrap up conservation of energy.